In this topic number 3, we will be discussing the thermodynamic properties of a particular working fluid. That working fluid is what we call a pure substance. It is of special interest for us to have a topic of this. For this particular substance, it's because many devices, or maybe not many, but rather um, common devices and systems, like for example the steam power plants, and also the refrigeration systems, those working fluids that travels all throughout the subcomponents or the entire system is actually what we consider as a pure substance. That is why we have this week of allotted time for these thermodynamic properties of a pure substance. So for the contents of this topic, we will first have an introduction, the application of, or the importance why we to study this topic. Then number two, we'll have a description of what a pure substance is. Then for number three and number four, we'll talk about the phases and the change of phase of a pure substance. And number five, we will introduce this PVT surface, or that's the pressure, volume, and temperature surface, and its projections later on. And actually, it's a way, or a tool of knowing where that state or condition or phase of a pure substance at the given condition. Okay, and then next is the states and regions, and number seven is the property data. So that means how do we obtain those properties, or where can we get those properties, such as the pressure, enthalpy, temperature, and so on. So particularly, we will be using the property tables. Okay, so for the introduction, so many devices or systems have their working fluids classified as a pure substance. Right here, for example, in a steam power plant, the steam is the working fluid, and that steam is just recirculating through these components or basic components. So we have here first the boiler. That boiler converts this liquid water, into steam, and that steam travels through the pipe, and that steam will enter this steam turbine. So when I say turbine, we have here a rotational shaft. So the energy in the steam will cause these turbines or the shaft to rotate. So that means we have this mechanical output power here. And if we attach an electrical generator, and that means we can have an electrical output as well. So steam will enter the inlet, and then will cause this shaft to rotate, and then it will exit at this point, and it will exit at some properties or at lower pressure, because some of the energy is already transferred to rotating the shaft, and steam will enter this condenser device. That condenser device converts the steam into a liquid water phase. Then from that liquid water, it will be pumped again to the boiler, and the cycle goes on. Okay, so the working fluid, whether it is in steam phase or it's in liquid water, it's actually a pure substance. Okay, so next one is the refrigeration systems. So refrigeration systems, how do we get this cold environment inside? It's because of these components. So it's just like the steam power plants, where we have components and we have working fluids. So just like there, we also have components here in the refrigeration systems, and there must be a working fluid as well. That working fluid is what we call refrigerants. That refrigerants is actually considered as a pure substance as well. Okay, so we have here the evaporator. So that evaporator is actually, that's what is causing this, or that's what's making the inside temperature colder. So it absorbs the heat from the inside, let's say from the food, so it absorbs the heat there, and then it transports that energy to this condenser at the back. So the right here we have condenser at the back of a refrigerator, and we feel a warmer temperature here. So that means there is a heat output from this condenser. Okay, so the circulation is through the this component called the compressor. Then we also have another device here, the expansion valve. So anyway, the point here is that the the refrigerant that's working or that's going through each of the components is actually a pure substance. Okay, so now let's define what a pure substance is. Pure substance is one that has a homogeneous and invariable chemical composition. So throughout the phases. So let's say water. So water, so it can exist in solid phase. Let's say an ice, and it can also exist in its liquid state. So just the liquid water, or it can exist also in its vapor state. So we have this steam right here. So whether it's in solid, liquid, or vapor, the chemical composition is the same. So it's still H2O. So that means it is a pure substance, or that's what pure substance means. So if we consider refrigerants, whether the refrigerant is in liquid or in vapor state, the chemical composition is still the same. So that's why it's considered as a pure substance. Okay, so furthermore, we will consider only simple, take note of this, simple compressible systems. So which means that the effect of electrical, magnetic, and surface tension effects are negligible. Okay, so now right here in the slide, we have an examples of non-pure substance. So there are also working fluids that are not considered as a pure substance, like for example air. So air is actually a mixture of dry air consisting of various gases. So we have nitrogen of I think 79% or something, then oxygen plus all other gases here, and plus water vapor and contaminants or solid particles. So if we just say simplify, we just say consisting of dry air only and then water vapor. So this is not a pure substance in especially at lower temperatures, because at lower temperatures the water vapor, let's say we have this cold surface and we have this air um, passing over this surface. So the water vapor in the air can condense at some cold temperatures, especially at the dew point temperature. So it will condense. It has the composition or the chemical composition is no longer the same. So that's why here we have these water vapor droplets, but at this or at lower temperature, it's no longer the same. There's no, or there's less water vapor, right? So it has a change in the chemical composition. Okay, another one is the combustion gases. So combustion gases, let's say it's a mixture of air plus, of course, combustion. That means we have these gases of, let's say, CO2 and some other gases, and also for gasification process. So we have here biomass fuel. It's being converted into gas. So from solid fuel, because of this process, thermochemical conversion process, that it is converted to this gas, and that gas is what we call actually a producer gas. And that producer gas is actually a mixture of many other gases. So CH4CO, H2. So it's not a pure substance, but rather it's another classification. Okay, so basically we just divide matter into just a pure substance or a mixtures. So pure substance just consisting of whether it's a pure element or a compound, like for example the H2O. And mixtures are those that are not pure substance. Okay, so next one is the phase of a pure substance. The phase of matter is a quantity of matter or a pure substance that is physically homogeneous. So we have here, when using H2O, we have here the solid phase, liquid phase, and vapor, and also the plasma. Although just included it here, we're just limited, or we will limit our discussion to this solid, liquid, and vapor. So in terms of these microscopic structures, we have these a you can say a rigid lattice structure for the atoms. But then, if it's being heated up, or if energy enters this substance, then that means some of the bonds will be broken down, and therefore it will change to this microscopic view, wherein these molecules, they have this free movement. And then, how much more if we add some more heat or some more energy into the substance? So we have these random motions or faster movements of these molecules. Okay, so that is what we call the vapor or the gas. So for now, let's just say vapor or gas, but later on there is a distinct difference between this vapor and the gas. So the change of phase from solid to liquid is what we call melting, and the change of phase from liquid to solid is what we call freezing or solidification. So freezing. Okay, so from liquid, the change of phase to vapor is what we call evaporation. And this one is what we call condensation. And there is this process from solid to vapor, that is what we call sublimation. So that means starting from solid phase, it doesn't undergo to liquid phase anymore, but rather change directly to vapor state. So that process is what we call sublimation, and the reverse is what we call deposition. Okay, so here the change of phase. So change of phase actually happens because of the addition or removal of energy in the substance. So when we heat up a substance, let's say water, let's say from ice, so from its solid phase we add heat. So that means, let's say first is, if we consider at negative 5 degrees C. So if we add heat, or if we add energy through the heat transfer or modes of heat transfer, so it will actually first is, let's say from negative 5, it will change its properties, it will increase its temperature, so until it gets to this point here, to the freezing point. And then if we still add some more heat, then from this freezing point it will actually start to change phase from solid to liquid. Okay, so notice that this change of phase actually occurs at a constant temperature, so there is no change of temperature at this process. Okay, so right here it's going to be fully liquid. So here is fully liquid. Right here is fully solid. And somewhere in between it's going to be a mixture of solid and liquid, because some portions of this ice still is solid, and some other are already converted into liquid. So if we still add some more heat, then it will start to increase the temperature again. So you see here we have an increase in temperature, or a change in temperature, until it gets to this boiling point. So let's say the boiling point here is 100 degrees C. So this is still fully liquid, but then the addition of more heat will cause this liquid to change phase from liquid to vapors. Right? So liquid to vapor. So again, notice that the change of phase happens at a constant temperature, say 100 degrees C and 0 degrees C here. So further heating will cause this change of phase from, say, fully vapor. So for now, let's just use the term fully vapor. Then right here, it's going to be another, actually, it's another term called the saturated steam, or superheated steam. So all this change in temperature and change of phase, it's because of the addition of energy. Now there is this term when referring to, say, right here, when referring to the change of temperature, that's what we call the sensible heat. Okay, sensible heat. And then the heat referring to the change of phase, right here, this is what we call the latent heat. Okay, and specifically from solid to liquid, we have this term latent heat of fusion, and from liquid to vapor, we have here the latent heat of vaporization. So that's the amount of heat to fully convert this liquid into, I mean, from this point to this point. Okay, so that's the change of phase. Again, it's just we're just having an overview of um, the the phases or the change of phase because of the addition of energy, addition or removal of energy. Okay, so now we will introduce this PVT surface. So the PVT surface is actually a surface plotting this pressure, let's say pressure, temperature, and volume. So when plotted, so depending upon the type of substance, or for example, the water, that is the type of substance that expands upon freezing. So that means the volume expands when it freezes. So it's being plotted here, and it's a 3D surface. But then somehow we can actually see the region of, I mean, where's the point where it's going to be solid, or where's the point where it's going to be liquid or vapor or maybe a mixture. So it's all here in this PVT surface. And then since it's a 3D, that means if we project only two properties, let's say pressure and temperature only, so we get this pressure temperature diagram. And if we project this pressure and volume, then we'll get a pressure volume diagram. And for when we project from the top view, so what we see is a temperature and volume diagram. So it's actually showing the same thing, except that in each particular view we get a maybe a more pronounced information. So for example, here in this pressure and temperature diagram, this is sometimes referred to as the phase diagrams, because all of the phases here can be shown directly, or it's more pronounced to see the phase change when using this pressure temperature diagram. Okay, so now in detail, here's the pressure temperature diagram. So projecting from the pressure and temperature, or from this view, so what we get is this pressure temperature diagram. So what we see here is this line. We have this this line right here, and also this, and also a line from solid, right? So, and meeting at this point. So the curve here is what we call the sublimation curve, and this point right here is the vaporization curve, or the saturation curve later on. And then here's the fusion curve. So you will notice that there's actually an intersection point here, that is what we call the triple point. And also here we have this point right here, that is what we call the critical point. Okay, so take note that these are just points wherein at least somehow we will know, or we can get some information from it. So let's say for the triple point, that is the condition or the point wherein both the solid, liquid, and vapor can coexist at that condition. So they exist simultaneously in this triple point. And then right here we have this critical point. So it's termed critical because somewhere beyond this critical point, there's actually no distinction between this liquid and the vapor. So especially here, the pressure corresponding to this critical point is what we call the critical pressure, and the temperature corresponding to this critical point is what we call the critical temperature. So beyond here, beyond the critical pressure and temperature, so the the phase or the region of this of the substance is what we call actually supercritical fluid, because there's no distinction between a liquid and a gas. Okay, so that's beyond this critical point. So if we consider only the temperature, there is this distinction between gas and vapor. So we use the term vapor when we are referring to the state of substance below this critical point. So that's what we call vapor, and then gas is the term when for the state of substance that is greater than the critical temperature. Okay, next is when using this PV diagram. So shown here actually is just this. We didn't include this solid region right here, so I just cut the this diagram. So showing only this liquid vapor region and the liquid and the vapor region. So here it is. We have here this curve. So that's the same curve right here. That is the saturation curve. And our critical point is right here. So here's our critical point again. So from this critical point going to the left, that's what we call the liquid the liquid region or the compressed liquid region, and to the right is the superheated vapor region or the vapor region here. Okay, and then inside, that's the mixture of liquid and vapor. So that means the liquid and the steam or the vapor actually coexist here. So we call this saturated liquid vapor region or mixture. Saturated mixture region. Okay, and then we have these lines. So here's the lines. So this is what we call the temperature lines, wherein temperature is constant. So here temperature is constant, and then another line here, temperature lines. So another, let's say this is T1, this is T2, and it's constant. Okay, so I think the increasing temperature is going this way, but then the reading is like this. Okay, the next one is the temperature volume diagram. So when projecting from a top view, what we get is a temperature and volume diagram. So it's almost the same. So it actually looked the same, but the lines here, so since this is plotted in temperature and volume, then the lines here corresponds to the pressure lines. So pressure lines, or let's just say P is equal to C, then another pressure lines right here. So increasing pressure goes this way. So that means when you say the boiling point of water is 100 degrees C, that is only true for P is equal to 1 atmospheres, right? So that means it will change if we have another pressure value. Okay, so I think that's all for these diagrams for now, because later on we'll have a detailed discussions about this information inside this diagram. So just to have a review of what we have discussed so far is first we talk about the introduction or the applications of this pure substance, and one application that we have discussed here is the steam power plant and the refrigerator device. Then we discussed what a pure substance is, and we say that it is one that has a homogeneous and invariable chemical composition. So that means in whatever phases it exists, the chemical composition is the same. And then we talk about the phase of a pure substance, and we talk about the solid, liquid, and vapor phase. And the change of phase, we have this term here, let's say melting, evaporation, and here freezing and condensation. And from solid to vapor, we have this process called sublimation, and the opposite process is what we call the deposition. And then we introduce this, or we discuss this change of phase. So again, there's a change of phase, or there's a change in the properties. Actually, it's because there's energy that entered this substance. So it could be from heating, or it could be from mechanical work. So there is actually a change of phase. Commonly, of course, it's on heating, but again, it's the energy actually. And then we introduce this PBT surface. That surface represents the pressure, temperature, and volume of a substance. And in this example, we use the substance that expands upon freezing, and this is the PBT surface. So we project this this surface, let's say from this side view, and then from this front view, and then from a top view, and what we get are these specific diagrams. So in that specific diagrams, you can actually get informations from the face, I mean, of the phases of a substance. So at a pressure condition, or a pressure temperature condition, or pressure volume and temperature condition. And right here we have this point that I highlighted, which is the critical point, and this triple point. And that triple point actually is at that condition, the solid, liquid, and vapor coexist at that condition. Then in this critical points, beyond here, there's no actually distinction between the liquid and the gas phase. So we call them a supercritical fluid. So that's above the critical pressure and the critical temperature. So if we are only referring to, let's say, below the critical pressure, but then above or beyond this critical temperature, the substance is what we call gas, and below the critical temperature is what we call vapor. So there's actually a distinction, or there's a difference between a gas and a vapor. That's why for water, we only use we use the term vapor because we are in below this critical range. So steam or vapor, superheated vapor. So it's just vapor, so it's not actually gas. So gas are those like, for example, the oxygen, the methane. So those are the gases. By the way, I mentioned about this these gases right here. Although this is also a pure substance, I mean, by itself we can, I mean, somehow it can be modeled maybe as a pure substance because we have these stable properties for this. But the mixture is actually not. So that is why. That's why it's a mix. It's a mixture because there's a lot of gases, individual gases here. Okay, and then next one is the. Okay, so I think that's all for now in this video. We'll continue our discussion in the next video.